So we just heard about unified sparse formats, and now we're going to be unifying other stuff. Maybe two very different meanings of unification, but take it away, Edward.
Yes, significantly different meanings of unification. So my name is Joachim. I'm just starting on my second year of my PhD, and I'm in Oslo. And this is joint work with these two other guys, Robin and Michael, who are from Denmark. And yeah. All right, and then just to give a brief overview, I'm going to motivate something that has to do with the unification, and I'm going to use program inversion as the motivation for the work I am doing. And it's something that's very closely related to other research that I'm also working on. So then I'm going to give you a program example, and then I'm going to give you a simpler program example in the interest of saving time. And then in the end, we'll discuss what one can do with this example. All right. So program inversion, there are two questions that might pop up. The first one is why? Why do you want to invert a program? Well, so I just came up with a couple of bullet points, right? So if you wrote an encode algorithm, then the inverse program should of course be a decode algorithm that fulfills this equation. And it's silly to write both programs if your compiler can generate either or the other, right? So, but you might also imagine sort of a semi-inversion. So let's say you have an algorithm that encrypts something, and it takes two arguments. It takes a key, and it takes input, and then it outputs a gibberish, right? And then you have a decrypt algorithm that takes a gibberish and a key and outputs the data. And so it's a semi-inversion where you take something from the input and make it an output, and something from the output and make it an input. Then something that's more closely related to what I do, you might imagine that you have a test case, and you sort of run it on a handful of examples. Let's say you run test on 0 and 1 and -1 and maybe 47 and some big number. I don't know what the edge cases are. And then you sort of say, oh, then it probably works for all of them, right? But if you have an inverse program on test and you run on test on false, it'll give you a counterexample to the statement for all x test of x. Right, which is significantly stronger. So it's useful in sort of various areas, from verifying programs to saving time on writing several programs that do almost the same thing. So the other thing you are probably asking is how. And I also came up with a handful of bullets, or 3 bullets, to sort of just suggest ideas. Right, so the first one is invertible programming languages. And there's a huge body of knowledge on how to do that. Essentially, now I saw a bunch of you work on sort of imperative programming languages, right? And there you might have an operation plus equal that sort of changes the state to increment the value of some variable, right? And if the thing you increment does not contain that variable, then minus equal is of course the function that makes the state transformation isomorphism, right? And so you can give the programmer plus equal precisely because you also give him minus equal, or her. And then what else? Well, you could make a relational intermediate language. Why? Because relations are significantly easier to invert. Right, so if you have a relation from A to B, you can just sort of move the B to the input side, and then you sort of have a relation from A times B to unit, right? And it can just sort of contain all of the pairs that were related, and vice versa. So sort of pure relations are at least finite pure relations are trivially invertible. And then, of course, you can design something. Right? You can make a combinator library and then say, okay, so long as you use these combinators, I promise you that I can invert your program. Right? If you do something else, you are on your own. Right? So it's you design something and you give it to the program. All right. And then just sort of to cover some ground, I picked two important ones. The first one is this Torben Egidius Mogensen, who studied the guarded equations programming language, and it's sort of like your garden variety functional programming language. So sort of a function is sort of the name and an expression and a guard, and it's sort of equal, and then there's a function body, which is also an expression. And then the question is how to invert those, right? And so if you only have product types, right, then you can draw very nice sort of string diagrams, right, and you can sort of pick the arrows that go into the program to be the inputs and the arrows that go out of the program to be the outputs. And then flipping one arrow we call a semi-inversion. Right, so let's say you just take an output and you make it an input, right? And the way to construct this inverse program is to just test, so run the original program and then test that this extra input is actually the thing you would output if it was on the other side of the relation. Right, and of course, if you invert all of the input arrows to be output arrows and all of the output arrows to be input arrows, then you get an inverse program. So in that sense, constructing an inverse program is just a special case of semi-inverting a program. And one way to do this is that you can take the original program, which is then some equations, and then you can sort of just consider them as unordered relations. And then you can perform refinements and try to re-sequentialize them, right? And sort of you don't really know when this works and when it doesn't work, right? But if it works, then you get an inverse program. So it's not very satisfactory. But then in 2015, some clever guys from Copenhagen came up with a programming language called RFun, for Reversible Functional Programming Language. And so this is sort of an example program written in RFun. And it takes a list as its input, and then it outputs the elements of the list in the reverse order. And it does so sort of in the way you would expect, only that there's a let statement and there's this special rlet statement that unruns a function call. And so the interesting thing is, of course, what are the semantics of rlet? And I brought them with me. So let's just talk about rlet for a second. Right, so rlet is sort of, the judgment form is in some environment, right, given some expression, it evaluates to something, and then the environment is on the left-hand side of the turnstile, the expression is between the turnstile and the little squiggly arrow, and the thing it evaluates to is on the far right. And so in RFun, we require that environments are actually disjoint unions, so programs are linear. Not in the linear algebra sense, but in the sense that every time you bind a variable, you must use that variable precisely once in your program. Right, and so it means that any variable that occurs here cannot occur here. Right, because they are sort of bound outside, and it can only appear once. Right, and so, well, it's almost what you would expect. So the result of rlet is Lin, right? The input to the reverse computation, and the output is the argument that you give to the function, right? And then, first of all, you need to figure out what the f it evaluated to, right? So, but you know that if you compute the most general unifier of that value and this pattern that you have, right, then you should get this part of the environment, sigma in, right? And so the inverse interpretation of this rule here really says, right, if you take this environment and apply it to the input pattern, you get a value, right? That was the value that f was called with, right? So this rule you read that way, right? And all of these rules you can read sort of depending on what parts you have. Here you also don't have sigma out, but now we have v in and L out, right? So again, you can unrun this rule, and then this rule you can run in the conventional direction, right? And so you'd think, oh, so that's how to implement reverse computation. but it turns out it's not, because the semantics of the case statement also become more complicated, right? And so how does the case statement become more complicated? Well, every time you make a choice, if you want to uncompute it, you have to know which choice you made. So the judgment rule for the case statement has been extended. So it says what you think it would say. Right? The case statement has a selector, and then it has sort of a list of patterns, right? And a list of expressions. And the first pattern that it matches, right, it'll compute that expression. But it'll just require this extra thing called a symmetric match policy. It says that sort of when you then look at the output expression, right, that has to end in a value, right? And if you match the result with all of the patterns in the end of those case statements, right, you must match precisely the branch that you came out of, and otherwise you get a runtime error, right? Which is also a little bit unsatisfactory, right? But furthermore, it's actually really slow, right? And the reason that it's really slow is because now you sort of have to infer, when you uncompute a case statement, where you came from. And you can sort of be crawling up a branch and then realize, oh no, this is not where I came from, and then you have to backtrack. What can we do about that? Well, we can look at how we do backtracking in relational programming languages, and I picked Prolog. And so I wrote a Prolog program that does some backtracking. You can also just interrupt me if you have a question. That's fine by me. So I wrote a Sudoku solver in Prolog, and luckily it fitted in a slide. So that's what it is, right? It takes a list of lists as arguments, and I will call that sort of the rows, right? And then the length of that list is sort of something, right? But it's not something I took as argument, it's something that I bind on my way out, right? And then sort of transpose is something I can do to get the columns, right? And then I have this domain unification, right? The indices has to unify with something in the domain of the number from 1 to n, right? And yeah, you know the game Sudoku, right? And I implemented this thing, and so here it is. And I also implemented it in Haskell, which is a functional programming language, and those are the two things we are comparing currently. So here is a Sudoku solver written in Haskell, and here is the one from the slide. And then I have also defined variables problem 1 and problem 2. And just to clarify sort of so in a functional programming language, you cannot do this trick of unifying something and waiting for it to be something later, right? But you can have lazy evaluation, which sort of means, well, you can defer computing what something is until the very last moment that you need it, right? But you cannot just return a free variable and then say, well, the result is, you know, all of this, and then I don't know what should be over here, but I'll call it x. Right? Then you'll get an exception, unbound variable exception, like in any other programming language. So this is sort of, evaluation by constraint solving, and this is evaluation by term reduction. So that's the key difference. Right. Okay, I also brought 2 examples. You can manually verify or just trust me that they are the same 2 examples, right? And hold my friend. All right. So sort of just, I'm not trying to hustle you here, right? This Prolog program really solves those 2 Sudokus, right? And they are full of free variables, and this underscore syntax in Prolog just means a fresh free variable. They could be sort of just x5, x7, x9, right? And likewise, the Haskell program Also hold my friend. Have to remember the extension. There are 2 files in that folder, sudoku.pl and sudoku.hs. That's what the problem was, right? So, so let's run it on problem 1, right? And it solves that, and then let's run it on problem 2. Oh, damn it! It doesn't really. Oh, it does actually stop with a solution for that, but we don't have time to wait for it, right? And so the question is, why do we have to wait so long for the term reduction when we don't have to wait for evaluation by constraint solving when they are essentially the same algorithm that we typed, right? And well, so here is the first row says 0, 0, 0, 0, 0, 0, 0, right? And if you just start by making guesses, then you'll have some computation that starts by making 9 branches, and then each of those make 9 branches and becomes humongous, right? But if you sort of solve that to do by hand, you will sort of write all of the constraints, and then suddenly you'll have a constraint that says, now I know exactly what you should say there, right? So that's really the difference. For intuition, what is the difference? That's the difference. Okay. So just to do something that we can finish in time, I also brought a simple example, namely a program that sort of just swaps 2 arguments in a pair. Right? And so here's a Prolog program. It takes a pair and returns the first element, takes a pair, returns the second argument, takes a pair, swaps the arguments. And then there's a Haskell program that does exactly the same thing in exactly the same way. The Prolog program, I can invert freely. Right? For instance, I can call it with a free variable as the input, and then I get the output, right? Or I can call it with 2 incomplete pairs, right? And then get the variable bindings deeper that sort of complete the pattern, right? Unfortunately, I cannot do the same thing with my Haskell program. And what is the reason for that? Well, sort of here, I threw something away, right? You cannot invert something that deletes something. So here's a program, it deletes a file, and then please undo it, right? And it's sort of, no, the file is gone. So, so what can we do instead? Well, the best we can do is to return a free variable. So here, or sort of in our work, we sort of introduce variables and do variable bindings as separate concerns. Meaning, sort of, now you can just say there exists X, and then later, your computation will require that you say what it is, right? But unless someone really needs to use X for something, it can just be a name, right? And so doing that, I can have my pair P1 question mark, which is sort of the result of inverting first, and I can have my variable P2 question mark, which is sort of the other way around, right? And then I can get my pair by unifying those 2 structures, precisely as we did with the Prolog program. It's a very precisely the same thing, right? And so this operation is really something that takes two things that are structurally equivalent, right? But they contain variables not necessarily in the same places, right? But when they contain variables somewhere, you compute some substitution and you apply the substitution to either. And then you get the resulting data structure which does not contain any variables anymore. And so that's what the trick is, right? And so thank you very much. And if you have questions, fire away.
So we can take one question. I'm sorry to be so brief.
Okay.
I'm sorry.
Yeah, no problem. Build it only.
If there are no questions, I do have one.
Okay.
So I was wondering, in terms of expressiveness, how would it be different than non-recursive data loop, let's say? So for example, I do union of conjunctive queries which have also existential quantification.
Yeah, so in terms of expressiveness, so in terms of expressiveness, it's not more expressive, right? If you make a computational system that you can express the inverse function of some function, then you can do so, right? But it's more efficient.
I see. Okay.
So there's a sort of, if you have a function and you know it's an injective function, for instance, right? Then you can just sort of enumerate inputs until you find the one sort of, oh, I know that f of x is equal to y for some x, right? So I'll just sort of iterate through them, right? But that computation will never finish.
Yeah, but let's say if you have a finite domain, and then, so let's say a kind of query processing engine, the data, for example, for evaluating conjunctive queries, basically it uses some sort of index and these kind of things. So would it be definitely more efficient than a data look engine in that sense? Let me rephrase it in another way. So what do you think is there that doesn't exist in data look engines, for example?
Yeah, okay. So in a functional programming language, you can really express something that's not a relation at all, right? And then sometimes you need to do this unification operation. Right? So it's sort of, if you look at functional logic programming languages, such as the verse calculus, which is this Simon Peyton-Jones paper, which was released last year, then you are sort of figuring a way to factor out what the choice is, and then inside of computations that don't make a choice, you can just do term reduction, which is much faster, right? And also, if you don't need to make a choice, then you don't have any problems. Right? It's sort of so it's sort of the thing that's not there. The thing that's there that's not in existing work is the separation of concerns, right? It's the treating variables that are sort of, for the purpose of unification, differently than other variables.
Okay, thank you.
You're welcome.